Miranda, for those who don't know me. We're going to have two talks, two 40-minute talks, 30 minutes plus 10 minutes for questions. The first talk is by Rodrigo Pereira from Natal, spontaneous spin chirality versus magnetization in a zigzag chain. So, please, Rodrigo.
Okay, so hello everyone. And first let me thank the organizers for inviting me. I'm really grateful for being back in São Paulo and seeing so many friends together again. So I want to tell you a story about the competition between two different types of order. And what they have in common is that they both break time reversal symmetry. So let me start with some general remarks about time reversal symmetry in spin systems. So we're going to always talk about Mott insulators here. So just think I have some Hamiltonian for some defined in terms of some spin operators on some lattice. And we know that time reversal symmetry is an anti-unitary transformation. So it involves complex conjugation. And it acts on spin operators as flipping the sign of the spin operator. So if you want a Hamiltonian which is time reversal invariant, and it's Hermitian, so there's no factors of I, the constraint of time reversal symmetry is very mild. You just have to write down something which is only involves even powers of spin operators. And besides time reversal symmetry, we often are interested in Hamiltonians which have some spin rotation symmetry, which can be either continuous or discrete. So here I have, for example, some models with SU2 spin rotation symmetry, which will involve the Heisenberg interaction, but also you can have four spin operators, ring exchange type terms. But you can also be interested in some models which have some just discrete Z2 spin rotation symmetries, like an XY Z model on some lattice. And we want to talk about ways in which we can break time reversal symmetry. And the most familiar way to do this is, of course, magnetic order. So we know if you have some ground state which has a non-zero expectation value for the spin operator, that will be the magnetic order parameter. It can only be non-zero if you take the expectation value in a state which is not invariant under time reversal. So one example here would be the Néel state, which I illustrated over there. So, and then we know that in this case of, let me take the Néel state as the example, if we break, if you have magnetic order, you break some spin rotational symmetry, SU2, for example, we also have to break time reversal symmetry. However, the opposite is not true. We know that we can break time reversal in spin symmetry in spin systems without having magnetic order. This is known since the 80s, this paper by Wen, Wilczek, and Z, where they proposed this kind of order parameter for what they called Chirospin states. So this would be some kind of order parameter for an SU2 symmetric spin system. So if this has a non-zero expectation value, you break time reversal symmetry because it's a three spin operator, an odd number of spin operators. However, since this is a scalar, it will not break spin rotation symmetries. And when this happens, I'm going to refer to this kind of state as a Chirospin state. And here I have three different spins which can be defined on any lattice which has some triangular plaquettes. Just take any triangle. So let me give you some examples of states that do this. Okay, so, oops. Yeah, so one example would be what happens on the Kagome lattice. If you take a Heisenberg model with first, second, and third neighbor interaction, I'm borrowing here the phase diagram from this paper, where they say that there is a chirospin liquid phase here. This would be a gapped spin liquid with topological order. It has a billion anyons. And this is a state where you have non-zero scalar spin chirality on the triangles of the Kagome lattice. And let me also draw your attention to the fact that there are some other phases around here. And you have here some transition from this chirospin liquid state to the Q equals 0 magnetic state on the Kagome lattice. This is a coplanar magnetic state, so it has long-range magnetic order, but it does not have scalar spin chirality. So here you have some non-zero spin chirality, but no magnetic order. So you have some transition from both states that break time reversal symmetry, but with different order parameters and different symmetries. And they mention in this paper that actually the numerical data, this is the DMRG on cylinders, is consistent with a possibly continuous transition from one phase to the other. This would be strange because, from the Landau paradigm, you would expect first-order transition between two ordered phases with different order parameters that break different symmetries. So if this really happens, you have to be something exotic along the lines of the confined quantum criticality, and I'll come back to this point at the end. Just to clarify the terminology here, I'm going to distinguish between chirospin states and chirospin liquids. I'm going to use chirospin liquids to refer to states that, in the gapped case, have topological order, anyons, and so on and so forth. But you can also have chirospin states which are not topological. They'll have a twofold degenerate ground state just based from breaking time reversal symmetry, but nothing more exotic than that, okay? Okay, maybe I should stand over here. Yeah, another example, which is actually closer to the kind of model I want to talk about, is if you have just discrete spin rotation symmetry, like in Kitaev type interactions, the kind of interactions that Eric talked about yesterday. So you can put the Kitaev model on a lattice with coordination number equals to 3, and it will be exactly solvable. So for instance, there is this Yelkivenso model defined on the star lattice, or decorated honeycomb lattice, if you prefer. And this model has two chiral phases, actually, because you can define different types of bonds. So you label every bond X, Y, and Z, but you take different coupling constants, different Kitaev couplings for the bonds in the triangles versus the bonds outside the triangles. So you can actually solve this model exactly in terms of Majorana fermions and find a transition between two chiral phases. One of them is topological, and the other one is topologically trivial. And here, to talk about chirality, I have to generalize this concept of scalar spin chirality that I showed before for ST2 invariant systems. So I'm going to refer to anisotropic chiralities as this kind of three-spin operator, which, of course, changes sign under time reversal, but it's invariant under the discrete spin rotation symmetries, like pi rotations about X, Y, or Z axis, which are the spin rotation symmetries that this kind of model has. So we wanted to look for this kind of phase in one dimension. So these are some questions that we asked ourselves. So we want to bring this kind of physics down to one dimension, because then we have more controlled analytical and numerical methods to study, for instance, transitions out of the chiral-spin state. And also, in one dimension, we have better chances of doing this with exactly solvable models. Also, we wanted to understand this competition between magnetic and chiral order parameters. They don't always compute. It's possible that they coexist, but we're going to look for a model where they compete and that there is a transition between these two phases. And in what sense they actually compete. And finally, we want to look for a continuous transition between these two types of phases, the kind of problem I mentioned before. And the answers to all these questions will be yes, but I should say up front that we're going to construct a model that does this. I'm not going to promise that it has any experimental realizations, so it's going to be tailored to answer yes to these questions, but it will be somewhat artificial. But the point is, we want to know that this kind of physics exists, it's possible, then perhaps it's realized in a more realistic model where we don't really have exact solutions. And this is the work of my student, Rafael Macedo, and also Flavia Ramos, who is currently a postdoc in Germany. So this is the plan. I'm going to show you the model and tell you about how you find a chiral phase in an exactly solvable limit of this model, and then talk about the transition to the magnetic phase that this model also has, and finally show you the complete phase diagram that we get from numerics. This will be the MRG calculations. So here's the model. We're going to follow this Kitaev route and define Kitaev interactions on a quasi one-dimensional system So we want triangles, so we start with the zigzag chain. But actually, we can start from this 4-site unit cell. So I have a square, and I divide the square into 2 triangles, and then I can label the bounds as X, Y, and Z, and put the Kitaev interactions according to these labels. And so I can have different couplings along the different directions. And also, I'm going to distinguish between 2 types of Kitaev interactions along the X direction here, Kx and Kx prime. This will be convenient later. I'll explain why. And from now on, I'm going to write the spin 1/2 operators in terms of Pauli operator sigma. And like I said before, in this kind of an isotropic model, we have to take this kind of 3 spin operators. These will be our chirality order parameters. And these are the specific ones that will be convenient here. So I take these operators on the up-pointing triangles of the zigzag chain, and these ones on the down-pointing triangles. So if you look at these indices here, they're labeled according to whether a site is opposite to what type of Kitaev bond. So there is some logic in this definition. So far, it's not that artificial because I could claim, okay, so there is Jacquet-Caliu mechanism on triangular lattice. This could be realized in some Mott insulator with strong spin orbit coupling. However, here, to get the phase I want, I will need this extra ingredient, a multi-spin interaction that couples, actually 6 spin operator that couples chiralities on different triangles. And I'm going to couple them like this for reasons that will become clear later. I only couple chiralities between nearest neighbor down-pointing triangles and separately between nearest neighbor up-pointing triangles. So these are the 3 spin operators, the chiralities that I defined before. So I just add this Q coupling for this chirality coupling. What about symmetries that we might want to break? So we have time reversal symmetry, as I already explained. Also, these Kitaev type models, they have some unusual type of spin rotation symmetry, which is actually sublattice dependent. So you can take a 4 sublattice pi rotation, which is generated by these unitary operators here. So what this does is, according to the sublattice index, you go and rotate spins in sublattice 2 by pi around the x-axis, around the y-axis for sublattice 3, and z-axis for sublattice 1. So it's local like this. It's unusual, but this you can check that this commutes with the Hamiltonian. And there are actually 2 types of operators like this. So there are 2 Z2 symmetries, and in this paper, this was called the Klein symmetry because this is isomorphic to the Klein group, Z2 cross Z2. And also, in terms of these generators of this Klein symmetry, I can just take the product of these 2 unitaries, and this will be simply just the product of sigma z on every site. So this is the generator of the global pi rotation about the z-axis, the usual spin rotation symmetry. I should probably stay here. Yeah. Okay, so let me just go. Yeah, so here. So let me start from the model which has these Kitaev interactions. And I'm going to look for exactly solvable points to say that this chiral phase and the magnetic phase exist. So one limit that we're going to take here is that, remember, I wanted to take kx prime here different from kx. So the simplest point here is just to set this kx prime to 0. And then you can see I switch off some bonds. And now I have this kind of lattice where each site has only 3 nearest neighbors with 1 x, 1 y, and 1 z bond. So this is now a one-dimensional lattice with coordination number equals to 3. So this Kitaev model will be exactly solvable on this lattice. So that's our first exactly solvable limit. And this model was actually studied before. It was called the tetrahedral chain in this paper. And I just took it, the chain, and stretched it, so it's going to look like this. And like I said, it's solvable just like any Kitaev model on this kind of lattice. And Eric already explained this yesterday. So you just have to write the Pauli operators in terms of 4 flavors of Majorana fermions, which can be represented like this. And then the trick is that you have this Z2 gauge field that involves 3 flavors of these Majorana fermions. They're defined on the bounds, and they'll be conserved quantities, local conserved quantities. So you can just fix the eigenvalues of these local conserved quantities to simplify the Hamiltonian. And the exact eigenstates here will be defined in terms of fixing these constants of motion. So yesterday, Eric called them fluxes. They're fluxes of the Z2 gauge field. In this context, since I have triangles, they can be related to the scalar spin chiralities. So whenever these fluxes are fixed, I have a non-zero expectation value of the 3 spin operators. So I have a chiral phase with this non-zero order parameter here. So time reversal symmetry will be spontaneously broken in this model. And yeah, so and besides these Z2 gauge fields that I constructed from 3 flavors of Majorana fermions, we also have the 4th one, which is going to be dynamical, the ones that are usually written in terms of C here. So they're going to move on this background of this Z2 gauge field. So like the Kitaev model on the honeycomb lattice, here you have these 2 types of excitations, fluxes and Majorana fermions. And the fluxes, the Z2 gauge field is static, and the matter fermions are dynamical. And then you can look at the excitations that we have in this kind of model. So you can start from some reference state where you have the uniform flux configuration or uniform chirality, like everybody is a plus sign for the scalar spin, for the anisotropic chirality. And the excitations would be to flip these chiralities somehow. And in one dimension, it will be convenient to think of the excitations as domain walls. So there will be kinks between 2 types of ground states with opposite chiralities. And we want to distinguish between 2 types of domain walls, which depend on whether I flip the sign inside the unit cell or between unit cells. So I'm going to call them intracell or intercell domain walls. And you can actually distinguish between them precisely in terms of the eigenvalue of this operator here. Remember, this is the generator of the global pi rotation about the z-axis, which is an unbroken symmetry in the chiral phase. It's going to be broken in the magnetic phase that I'll talk about before. And the first type of domain wall has eigenvalue -1 for this unitary operation. And the second kind has eigenvalue +1. And since this model is exactly solvable, we can actually compute the energies for the excited states, which contain domain walls, and estimate how they scale with the coupling constants of the model. So the intracell domain walls will have always a gap, which scales like the Kitaev coupling. I'm just choosing one of them to set the energy scale here, Kx. But the other type, the intercell domain walls, only have a gap if I switch on the 6-spin interaction. And that's why we need it. We have to pin the fluxes between different unit cells. Otherwise, if Q equals 0, you can actually check that this model has an exponentially degenerate ground state, which has to do with these local excitations where you just flip the signs of both chiralities inside a given unit cell. So that's why we added this interaction to fix this problem. But having done that, all the excitations are gapped. And you have these chirality domain walls and Majorana fermions moving on top of these configurations. And one important point is that if you compute the spectrum of Majorana fermions on top of these domain walls, there will be bound states. So there are Majorana bound states here, which have finite energy. They're not Majorana zero modes because this phase is not topological. We know for sure then there is at least one exactly solvable limit where you find this chiral phase. Remember, I had switched off this Kx prime coupling. So now I'm going to bring it back and look for transitions. And I'm going to start over here in this regime of strong chirality coupling and turn on the Kx prime interaction. And then once I have this interaction, I lose integrability. These fluxes or chirality domain walls become dynamical, so the problem becomes complicated. It's no longer exactly solvable. But at the level of first-order perturbation theory, what this does is to give mobility to the domain walls. And they will carry Majorana fermions as they move along. So these will be the important excitations that will control the transition to whatever lives out here. And the idea is that if I start cranking up kx prime, I get some bandwidth for these domain walls. Eventually, the gap will close, and you have some transition upon condensation of domain walls. And to figure out what happens in this limit, instead of sticking to the Kitaev representation, we found it more convenient to define pseudo-spin operators. So I'm going to switch from the original operators to another set of Pauli operators, which are defined like this. So I have now 4 pseudo-spins, 2 taus, tau 1 and tau 2, and 2 rows. The important point here is that the taus I construct, you can check that these obey the Pauli algebra and so on, right? You can check that the taus, tau x1 and tau x2 are exactly the spin chiralities, so they'll be the order parameters for the chiral phase, and the tau z will be the sigma x. So here I can associate a transition from the chiral phase to a magnetic phase depending on whether which component of this pseudo-spin acquires a non-zero expectation value. So this is the sense in which these phases will compete, right? So now they're chirality and magnetic order, they are 2 components of the same pseudo-spin. And you can rewrite the Hamiltonian in terms of this set of pseudo-spins. It comes out very ugly like this. But the point is, if you just look at the first line, the most interesting pseudo-spins here are the taus. I want to get rid of the rows, and the first line only contains row z, and row x and row y appears in the second line. So this suggests another exactly solvable limit if I set ky and kz to 0, which is to switch off the Kitaev couplings between the legs of the zigzag chain. Oops. Yeah, so that's what we call the highly anisotropic limit. In this case, I have another set of local conserved quantities, which I can fix to simplify the Hamiltonian, get out some degrees of freedom. And since rho z is actually, I forgot to point this out. Rho z is actually this 2-spin operator here, the product of sigma x between neighboring spins on the same leg. When I fix rho z equals to -1 for positive Kitaev couplings, I'm actually just saying that there will be strong antiferromagnetic correlations between nearest neighboring spins. And then once we fix this, we end up with this model, which only has one kind of pseudo-spin, this tau z's, defined on what now we can recognize as a ladder geometry. I have this index L equals 1 and 2. So 2 pseudo-spins per rung of this effective ladder model. And now we can analyze what kind of transition we can get out of this model. So first, I should say, I start from this limit where ky and kz are 0, but then you can go one step further, do perturbation theory to second order, and restore some effective coupling between the legs of this effective ladder. And the interesting point here is that now within this effective model, if this k perp, which is second order in ky, is 0, I actually get 2 decoupled xy chains. So the model is exactly solvable. And if I bring this back, this is like a leg with weak interchain coupling, which is also a good starting point for analytical approximations. So now we have to analyze this effective ladder model. And starting from this limit where k perp is 0, the model is exactly solvable. I know there will be a transition, just like the transition in the xy chain. When tau x is, when q is dominant, this is the chirality coupling, then tau x has a non-zero expectation value. This will be the chiral phase. But then if I start increasing the other coupling, eventually I will go through a continuous transition. And past the critical point, I have magnetic order because the other component of the pseudo-spin will have a non-zero expectation value. So in this case, for k perp equals to 0, I actually have 2 decoupled legs. So this is like 2 copies of the xy model. The critical point is described by 2 gapless bosons. So the effective field theory has central charge C equals 2. But this is a very special point. Okay, oops, sorry. Yeah, before I talk about the more general case, let me just point out some properties of this magnetic phase that appears on the other side. So you can now look at what tau z was in terms of the original spin operators and realize that this is some kind of magnetic phase which will have actually 4 ground states, which are represented here. So it now, since the magnetic phase, it breaks time reversal as well as a discrete spin rotation, and it also breaks the Klein symmetries that I mentioned before. And the fact that you actually have 4 and not only 2 ground states is related to the fact that some of these ground states are connected by this Klein symmetry. And it's also interesting to point out that the phase that shows up here, which has this order along the x direction, is a 1D version of what's called a stripe phase, which has also been found in the antiparamagnetic Kitaev model on the triangular lattice, where the phase actually breaks some rotation symmetries of the lattice. Yeah, so what about the nature of the transition? So I bring back this interchain coupling in the effective ladder model. And now the model is no longer exactly solved, but we can learn something by taking the low energy limit and analyzing the effective field theory. So you just bosonize this Hamiltonian here. And this is the Hamiltonian density written in terms of 2 bosonic fields. And the order parameters for the chiral and the magnetic phases are written as cosines or sines of the bosonic fields, and then by the way in which these bosonic fields are pinned, you can understand what type of order you get, what's the ground state degeneracy, and so on. And what you get from this interchain coupling is that actually this operator that appears here is strongly relevant, so you couple the degrees of freedom, the low energy degrees of freedom of these 2 legs, and actually lower the central charge, so at the end, instead of 2 independent bosons, you only get 1 boson at the critical point. So this will be a conformal field theory with central charge C equals 1, or a Luttinger liquid, if you wish. But an important point here is that this transition from the chiral phase to the magnetic phase will actually be described by a theory that has a continuous symmetry, even though we started with a spin model that only has discrete symmetries. So you have an emergent U1 symmetry. So then we went to look for this numerically. So here I'm showing you the DMRG data. We have done this both for the original model on the zigzag chain, also for this effective spin ladder model. So this here is as a function of this kx prime parameter. The order parameter for the chiral phase is the blue dots. And the green dots are the order parameters for the magnetic phase. So we have analyzed this transition not only by the order parameters, but some other properties that signal the critical point, like the energy susceptibility, the entanglement spectrum. They're all consistent with the fact there is only one transition from magnetic to chiral phases. And this suggests that it's really continuous transition. We can check that it's continuous because you observe scaling behavior in the entanglement entropy, for instance, and you can fit the central charge to the entanglement entropy and extract the value of C equals 1, which is consistent with there being a 1 gapless boson at the transition. Okay, sorry. And here's the complete phase diagram. And here I'm showing the phase diagram that we got for the ladder model. So here there is, the main part is that there is a transition from the chiral phase to the magnetic phase, which is described by the C equals 1 conformal field theory. Here I have a symmetry table, so you can check that the magnetic and chiral phases have different symmetries. So this will really be beyond the Landau paradigm. And also, there's actually a third phase in this phase diagram, which we're calling it a Klein symmetry breaking paramagnetic phase, or just Klein phase for short, or lack of better name. And this phase is only non-trivial because it only breaks this Klein symmetry that I talked about before. So it's not magnetic, it's not chiral, but it has a twofold degenerate ground state because it breaks the Klein symmetry. If you like, it's some kind of vestigial order of the magnetic phase because it has this composite order parameter, which is constructed out of sigma x and sigma x. And this does not look much like an order parameter. It's only an order parameter because we have the Klein symmetry, so you can do these sublattice-dependent rotations. And of course, to go back to the point I made at the beginning, I'm talking about transition between two different types of ordered phases. And that's against the usual Ginsburg-Landau-Wilson paradigm. When you talk about this, the first thing that comes to mind is this deconfined quantum criticality picture for the transition from the Néel state to a VBS state on the square lattice, this famous paper here. Actually, there are some strong analogies with this one-dimensional model. Let me just point out that in the original proposal, there are some important features to understand how you can get this continuous transition. And one important point that goes beyond the usual Landau theory is that the effective field theory for this transition must account for topological defects in one phase which transform non-trivially under the symmetries which are broken in the other phase. So when you condense the excitations that create these topological defects, you actually, this operator gets non-zero expectation value. You kill the original order, but at the same time, you get the other type of order emerging at one critical point, right? So these are usually described as very exotic field theories with emergent gauge fields and so on. And actually, that also happens in one dimension. There's some recent papers which discussed precisely revisited the Néel to VBS transition in anisotropic spin chains. And in this context, these topological defects are the domain walls of one phase or the other, which will then become gapless at the transition. And what happens in our case is that we have domain walls of chiralities, of the chirality order parameter, which trap these Majorana excitations, and these are the ones that will become gapless at the transition, and then you can understand also this transition in terms of nucleating the order of the phase which exists on the other side. Yeah, so that's what I have. So just to conclude, the point is that we found this continuous transition from a chiral phase to a magnetically ordered phase in this model, which is somewhat artificial. It contains K-type interaction, but also 6 spin interactions. But the point is that it shows that this transition can actually happen. There's also this other phase, which I didn't talk much about, that only breaks the Klein symmetry. And these phases and phase transitions are one-dimensional analogs of the confined quantum criticality. So thank you.
Thank you, Rodrigo. Thanks, very nice talk. So it's now open for questions. So let me ask you perhaps 2 questions. First of all, this last part, when you try to explain the quantum critical point in terms of topological excitations and so on, is there a duality between the 2 phases?
Yes. Maybe I can. Yes, exactly. And then this critical point is it's like the self-dual point.
Okay. As in 1D, it's very common.
It's
right?
very common, exactly. Yeah. It's not very hard to get. Okay. In terms of the other parameter, you can implement this duality. Remember, I had cosine and sine of the field, so you can just exchange them.
Okay, okay, great. Yeah. Thank you. And the other perhaps easier, quick question. Let me see, what was I going to say? Oh, you mentioned this thing where, not in your case, when you have one type of symmetry breaking, you don't have the other, right? You have a transition between the 2 phases. But then you mentioned that sometimes you have both at the same time. They don't compete. They
coexist, yeah.
But that's okay. That's normal, right?
That's normal, yes.
Because if you break magnetic symmetry, I think you automatically generate the other kind of symmetry, no? Because it's like not order parameter.
Yeah.
3D.
No, not necessarily. Break time reversal symmetry, but you don't get spin chirality automatically. Okay. Right? So it's like a 3-spin operator. Classically, it has to be something out of plane.
Okay.
Yeah. So the Actually, if you have non-coplanar magnetic phases, then you have both.
But in your case, it's not like this, right? Because it's
no.
X, Y, Z, and it's like
Yes,
discrete.
yeah,
So
it's discrete.
Okay,
Yeah,
but the
but
same applies.
In this case, yeah, the phase I was talking about, the magnetic phase has vanishing chirality and vice versa. Right?
Sure,
So,
sure,
yeah.
sure. Okay, you have more questions.
Hi. When you were talking about the transition, you said it was clear there was only one transition and that it was a continuous transition because you had scaling in the entanglement entropy. Or is there any other evidence that tells you it's really continuous? Because
we can also look at correlation functions along this line. Since it's supposed to be described by a gapless theory, you should see decay, parallel decay of correlation functions.
And what's the energy scale of the scaling, if you know what I mean? Is it over a wide region, or does it
you
cut
mean
off?
The phase diagram?
Yeah.
If I can go back. It's, yeah, so this transition, I'm drawing this kind of triangular phase diagram here, right? But you can see we have to walk along this line,
Yeah.
if that's what you mean. So it's a very...
But maybe I just missed it. On maybe it's the previous slide. Can you go back again? Where you have the actual diagram. Yeah.
Okay, yeah.
Yeah. Okay, it was that scale that I was missing. So
Okay, sorry. So yeah, this is the length scale. This
Yeah.
is the size of the partition.
Yeah.
So you have a finite chain, and then you take a bipartition,
And then
this is the usual CFT.
Okay, thanks. That's clear. Yeah.
So just a curiosity, when you have this deconfined contra-critical point, you usually have this sort of fractional excitations at this critical point. What would be in your case? Or
Yes, right. So in 2D, you only get fractionalization at the critical point, right? So like on both sides of the transition, you can understand the order parameters without using fractionalization. But in 1D, fractionalization is very easy, right? So you have usual Luttinger liquid stuff. So here already inside the phases, you have these domain walls, which carry Majorana zero modes. So in some sense, their excitations are already fractionalized. And then what happens at the critical point is that they become gapless, right?
Okay, on the other side. Let's cross the Atlantic here. I think the other one is...
Have you thought about generalization for two-dimensional system? For example, like the correlated lattice?
Yes,
because
exactly. Yeah, that's what we have in mind. I don't have any results, but my guess is that something very similar will happen there, because you can start, for example, from this topological phase, the Chirospin liquid. There you have the topological excitations will be vortices of the Z2 gauge fields. There are Majorana zero modes, and you can start breaking integrability and driving the system towards some magnetic order. Maybe something like this happens, right? So, but as far as I know, it hasn't been done yet, so it's just a guess. So.
Thank you.
So it's like perturbing the Yalke-Wilson model.
Thank you for the talk. How exactly would you expect the confining contra-criticality scenario to change if instead of spin halves, you have spin 1 or 3 halves in each site?
Yeah, I don't know if I have any insights on that. In principle, it's possible, right? Because it's the way it was understood originally, actually, there was not even a specific lattice model. So they analyzed it from the point of view of the effective field theory. So you start from whatever degrees of freedom you have on the lattice, right? Motivated by, of course, the Heisenberg model plus perturbations on the square lattice. And then you have some effective field theory with emergent symmetries and so on. So in principle, models with higher spin can also have this kind of transition. They could be even more exotic, right? It's like even higher symmetries, but I can't think of any example right now where this has been.
What's the role of frustration in this system? And in the confined criticality scenario?
Yeah. Here, see. In the original context, it was important in the sense that you wanted to destabilize the Néel state on the square lattice, right? So it's from Heiser plus something, which was like 4 spin interactions, ring exchange, and so on. They will drive the transition. It will frustrate the Néel state and drive the transition to the VBS. Here, our starting point has Kitaev interactions, which are, as defined on the honeycomb lattice, or even though the lattice is not frustrated, it has some frustration on the bone direction dependence, right, of the interaction. So it stabilizes chiral spin liquids, quantum spin liquids in general. Yes, and then we add some more interactions on top to drive the transition. Yeah. Okay. And also, you also have geometric frustration on top of that because it's a zigzag chain, right? So triangular geometries.
Sure. Thank you.
Thanks.
One last quick question over there. It's very hard.
So does it make sense to look at the free energy and its derivatives to further characterize this transition, to further check if it's continuous or? Yeah,
we looked at the ground state energy, right? So it's the transition at 0 temperature, and also there are signatures of the transition there. You take the ground state energy susceptibility, the derivative with respect to the driving parameter, and then there's a very clear peak at the same point here where the order parameters vanish. The derivative of the ground state energy with respect to this parameter, for example. No, actually, it would diverge in both cases, first order and second order, but then you can look for scaling behavior with system size, if it's continuous. Yeah.
Okay, I think that's it. Let's thank Rodrigo again.